Hi, I'm Rachita from CSC AML Section C. My topic is non-homogeneous equations in education. Let's enter into the topic. Introduction to non-homogeneous differential equations. A non-homogeneous linear differential equation has the form L of phi equals to f of x, where L is linear differential operator and f of x not equals to 0. Unlike homogeneous equations, non-homogeneous equations include an external forcing function f of x that drives the system dynamics. These equations model real-world engineering systems such as forced oscillations in mechanical structures and input-driven circuits in AI hardware. The general solution is the sum of the complementary solution and a particular solution. Y of x equals to y into c of x plus y into p of x. Understanding non-homogeneous equations is essential for modeling dynamic systems in AI and ML applications, time-dependent inputs. Classification based on forcing function. The nature of f of x determines the method used to find the particular function y into p of x. Common types include polynomial, exponential, sinusoidal, and pairwise continuous functions. For f of x, e power ax, the particular solution often takes the form y of p equals to a into e power ax. Adjusted for resonance, when f of x equals to sine omega x or cos omega x, the method of determine coefficients uses trial solutions involving sine and cosine terms. Discontinuous forcing functions, such as those modeled by Heaviside step functions, require Laplace transform techniques for solution. Method of undetermined coefficients. This method assumes a trial form for y of p based on the type of f of x. Unknown coefficients to be determined. For f of x equals to p into n of x e power ax. The trial solution is y of p equals to q into n of x e power ax, where y of n is a polynomial of same degree. If any term in the trial solution duplicates the complementary solution, it must be multiplied by x to ensure linear independence. The assumed form is substituted into the differential equation and coefficients are solved by equating like terms. This method is efficient for constant coefficient equations with smooth. Elementary forcing functions. Variation of parameters. General approach. Variation of parameters is a more general method applicable even where undetermined coefficients fail, such as with variable coefficients. It assumes the particular solution has the form y of p equals to u1 into x y1 into x plus u2 into x y2 into x, where y1 and y2 are solutions to the homogeneous equation. Functions u1 and u2 are determined by solving a system derived from the original ODE and an auxiliary condition. The W of y1, y2 plays a crucial role in computing u1 and u2 via integration. This method is particularly useful in AI system modeling where external inputs are not analytically simple. Laplace transform method. The Laplace transform converts differential equations into algebraic function equations in the S domain. Simplifying solutions of non-homogeneous equation systems, it naturally incorporates initial conditions, making it ideal for initial value problems common in engineering simulations. For equations with discontinuous or impulsive forcing, Laplace transforms provide exact solutions. The inverse Laplace transform yields the time domain solution using partial fraction decomposition and transform tables. This method is widely used in control theory and signal processing, foundational areas in AI and ML system design. Green's function and impulse response. Green's function g of x into e represents the system's response to an impulse point e. forming the kernel for solving non-homogeneous equations. The particular solution is obtained via convolution. Y into P of x equals to integration of g of x and e, f of e, t derivation over the domain. Green's functions are derived from the homogeneous solutions and boundary conditions of the differential operator. In engineering, Green's functions model how systems react to localized inputs such as heat sources or mechanical loads. This concept is pivotal in AI driven simulations of physical systems using neural operators and PDE solvers. Systems of non homogeneous ODEs. In vector form, a system is written as dx of dy equals to ax plus f of t, where a is a current matrix and f of t is the input vector. The general solution is x of t equals to x into h of t plus x into p of t, with x of h derived from eigenvalues and eigenvectors of A. For diagonalization, the particular solution can be found using matrix exponential or variation of parameters in vector form. So systems model multi-input AI systems such as robotic arms or sensor networks with external commands. Numeral methods like Ranskutta are often employed when analytical solutions are intractable. Applications in AI and ML. Non-homogeneous ODES model learning dynamics in neural network as f of t represents input data or training signals. In recurrent neural networks, as known as RNNs, the hidden state evolution resembles a non-homogeneous linear system with time-varying inputs. Differential equations are used to design continuous depth models like neural ODEs, where external inputs act as forcing terms. Parameters estimation in ML often involves solving inverse problems modeled by non-homogeneous boundary value problems. Understanding these equations enables better design of adaptive algorithms and real-time AI systems. Numerical methods for non-homogeneous ODEs. When analytic solutions are impossible, numerical techniques like impulse and Rajputta or multi-step methods are used. These methods discretize the domain and approximate the solution iteratively, handling arbitrary f of t effectively. Adaptive step size algorithms improve accuracy by adjusting step size based on local error estimates. In AI applications, numerical solvers are embe- embedded in simulation environments for training and validation. Software tools like MATLAB, SciPy, and Julius, differential equations JL or standard in engineering education and research. Boundary value problems with non-homogeneous transfer. Non-homogeneous boundary value problems known as BVPS involve differential equations with forcing functions and constraints at multipoints. Methods include eigenfunction expansion, where the solution is expressed as a series in terms of orthogonal basis functions. For example, y double dash plus lambda y equals to f of x with y of 0 equals to y of l equals to 0. Uses Fourier sine series to represent f of x and y of x. These BBPS arise in heat transformer, wave propagation, and structure analysis. Key areas in aeronautical engineering. Educational strategies and pedagogical insights. Emphasize the physical interpretation of f of x as an external influence, extends conceptual understanding among students. Use simulation rules to visualize solutions under different forcing functions and initial conditions. Integrate real world AI and aerospace examples to demonstrate relevance beyond theoretical mathematics. Encourage project-based learning where students model and simulate systems like drone control or neural dynamics. Assess understanding through problem sets that progress from analytical methods to numerical implementation and interpretation. Thank you.